Hmm. Okay, so what are we talking about today? I don't know how much time you have to look at these problems because I just posted them yesterday. But what I want to do is to introduce a concept that maybe you have not really seen yet. And the four problems. The first problem is supposed to be a relatively straightforward application of this algorithm, and then B, C, and D are a little bit more involved. They're a little bit, especially C and D, are a little bit unusual. So before I talk about any of these problems, I think what I want to do instead is to actually just talk about this thing called Fenwick trees. Okay, so I'll start by talking about what is this supposed to do, and then maybe say a little bit about the implementation, but that's not too important. You might also hear about some other places call it binary index tree. Okay, so what is this supposed to do? So suppose you have an array, have integer array A, and let's say of n elements, so from 0 to n minus 1. Okay, what do you want to do? You want to do these operations. These are the operations that you want to support. First operation is increment AI by a certain value. So, i.e., AI plus equals to V. Okay, you want to be able to do that. And two, you want to be able to retrieve the value. Okay. So far, you might say, well, what's the big deal? You do this with any arrays. But this is the third one that is important. What is the cumulative? Some people call it cumulative. Some people call it partial sum A0 plus A1 so where the input is I. So I give you an I, you tell me what is the partial sum up to that point. Okay, those are the three main operations. There are other operations that the code library version of this Fenwick trees also supports, but those are the three most important most important operations that we want to support. And if you don't have operations 3, then there's really nothing you have to worry about. You just use a normal array, right? You take the normal array, increment AI by V. Well, you just do exactly A bracket I plus equals V. And then if you want to know what is the value of A bracket I, you just go and look it up. There's nothing to it. One more thing. When I say increment AI by V, V can be negative. So you can kind of basically do decrements by providing a negative V. Now, the problem, of course, is computing the cumulative sum or partial sum. If you're just using a normal array, right, then how long is it going to take? Well, you got to add up everything from the first value all the way to I. And in the worst case, if you're asking what is the cumulative sum at the very end, then you're going to have to add this every single time you ask this. So if you do sort of naive implementation, this is big O of 1, this is big O of 1, and this can be big O of n for each operation. And the other thing about this Fenwick trees is we're assuming that you can do many of these operations. So you can dynamically update the array, then ask for what is the partial sum again, then you can update it again, by changing some values and ask for the partial sums again, and so on. Okay, so that's one problem. Now, what if you have to do something else? What if you actually just store the partial sums of the entire array, right? So let's start the next page. So imagine that my array is 1, 3, 0, 2, 1, 1. Okay, so it's a kind of easy array, 6 elements. Then I can compute a partial sum, which is just the sum of all the elements up to that point. Okay, so this is my partial sum. Then remember what are my operations. So operation 1, 2, and 3. So if I want to know what is the partial sum, well, that's easy. I can just look it up, right? You tell me which partial sum you want, you just look it up in this array, no problem. Okay, if you want to know what is a bracket I, well, assuming that you don't store this, okay, so assuming that this is actually not stored, you only have the partial sum, then you can also do figure of 1 because this entry, a bracket I, it's basically partial sum at I minus partial sum at I minus 1, right? So if I want to know what is this entry here, I take this number minus the previous number, that will give me the 2. Of course, I have to be a little bit careful. If I is 0, then I can't just subtract the previous one, but that's an easy special case to handle anyway. Okay, so both of these operations, 2 and 3, are easy. But what about operation 1? I want to increment a value. Now, this is going to be a big headache. Imagine that if I want to change this number from 3 to 4, how are the partial sums going to change? Well, all of these partial sums will go up by 1. And if you try to change a value at the beginning of the array, then you basically have to update the entire partial sum array. So updating a value is really, really bad. Okay, so this is also no good. So if you do the simple representation, just store the array, then you have the first 2 operations being easy to do. Last operation is horrible. If you store the partial sums, then the last 2 operations are easy, but the first one is horrible. So what is the solution? So here comes Fenwick trees. So before I actually tell you what it does, let me just tell you the complexity of each one. So updating a bracket I plus or equals to V, it is not constant time, but log n. Okay, so it's not the best, but it's not the worst either, something in between. What is the value of, so retrieve value of AI, it is also log n. And the partial sum, a bracket 0 plus up to a bracket I, it's also log n. Okay, so somehow we have a data structure that doesn't get you this constant time for any of the operations, but in the worst case, it's also not that bad either. Okay, so if you're doing a lot of these operations, if you're doing 1,000,000 of these operations, and n is, let's say, 1,000,000, then log n is not that bad. Whereas over here, if you use this one, for example, if you're doing a lot of operations and each one has the potential to be the worst case, then you can get really bad behavior. So in general, if you use the Fenwick tree, it will allow you to basically do log n per operation, which is very, very good. So before I actually tell you how this is internally organized, I want to show you the code. So I'm showing you the particular submission of one of these problems, but because in the beginning I just pasted the Fenwick tree code from our code library. So the Fenwick tree code, it's just a class. There's a constructor for this problem because n is 200,000. I just put it in there, but you don't have to. You can initialize the Fenwick tree for whatever number of elements you want to keep track of. Okay, so your Fenwick tree keeps track of an array of a certain number of elements. So the constructor just does that. Don't worry about how it does it. Then there's another constructor that will initialize not only, okay, what's the difference between these two? The first one assumes that you started with an array of all zeros. Okay, so all the partial sums are zeros, everything is zero. Whereas the second constructor basically says that you already have a value, you already have an array of values and you want to initialize that, okay, based on that array. Then you have something called increment entry. What does it do? It increments the entry of this index by this value. Okay, so you're incrementing not the partial sums, but the actual array value. And then the partial sum returns the value of the array from the first entry plus the second entry all the way up to this index that you specify. Get entry gives you the array entry at that location. So this is get a bracket I. And then there's this get index, which is a little bit strange. This way I haven't told you yet. But basically the idea is that if somebody if you want to know what is the largest index in your array so that the cumulative frequency is whatever is given. So what does that mean? So I have this, did I still have an array here? Yeah, so if I ask you, what is the entry of the index such that partial sum at I it's equals to 4, let's say, then it will give you, it will return 2 because that's the largest index such that the partial sum is 4. Okay, if you ask what is the largest index such that the partial sum is 5, it will tell you -1 because it's an invalid index. There's no index where this is true. Okay, well, I'm not talking about why we want to use that. Well, maybe someday we will. Okay, now there's also a little bit of complexity things here. If you want to use a second constructor, it takes n log n time, where n is the number of elements in the underlying array. Getting the cumulative sum at index k, it's log k, but of course k is at most n, so you can say it's log n. Getting the entry at a particular index is log n. Incrementing or decrementing entry, it's also log n. Given a value, find an index such that the cumulative sum of the positions that value turns out to be log n times as well. Space usage is basically double the size of the array. It's also assumed that all the entries in the array are non-negative, so you don't get negative numbers even after you decrement it. Okay, that is actually not completely necessary. It's only necessary if you want to use the last operation about finding an index that has a particular cumulative sum. Otherwise, you don't need this assumption. Okay, so Fenwick trees are data structures that allows the maintenance of cumulative sum tables dynamically. So when you look at problems where you're going to have a bunch of operations that kind of change the content of the data structures, and then you ask questions in between, and you interleave changing, updating the values, and querying all the time, then you need some kind, what we call dynamic data structure, which allows you to answer questions and update the data structures at the same time, both of them supporting both of these operations quickly. Now, if you read some of these code, let's just look at, I don't know, cumulative sum. You see some funny things. Okay, so there's an index here. While index is greater than 0, not a big deal. Sum is, you add a particular element in the array, and then you have this funny bit operation. This is bitwise and the index bitwise and with the number -1. What the heck is going on? So instead of telling you all these bit operations, what I want to kind of explain to you is how does this thing actually work in the internally. So to make things simple, I'm going to pretend that my arrays are size 8. Okay, usually it makes things simple. Size power of 2 is easier. And also, my array indices are 1 base. So my array indices are 1 to 8. Okay, so now I have in my tree, I'm going to have nodes in my tree. And I'm going to have nodes that store different things. So let me think about how I'm going to say this. So it's my tree indices. It's also 1, 2, 3, 4, 5, 6, 7, 8. So 1 base, this is my array A. So A, I might have values like 1, 0, 2, 0, 3, 1, 4, 1, 2. Okay, so this is my array A. And I'm going to have my tree also have an array of size 8. I think I do. I don't remember. Let me think. Okay, so I can figure it out on the fly. Okay, so these are tree indices, but I'm also going to store, I'm also going to at least write down for me to illustrate the binary representation of these tree indices. Okay, this turns out to be important. 7 and then 8. Okay, so now I have an array of size 8 for my tree. And what am I going to store in this array? So what do I store? Okay, what do I store? For 8, for the power of 2, I look at the power of 2, it's 8, and I just store the sum of everything. The sum of the first 8, first 4, first 2, and first item. So I just say A1, which is 1. And for second power, for 2, 2 is another power of 2. So I store A1 plus A2, which is 3. Okay, I skipped 3 for now because 3 is not a power of 2. What is 4? 4 is A1 plus up to A4, and that's 6. And then 8 is the sum of everything. So A1 plus up to A8. And that turns out to be what? 10, 14, if I haven't screwed up. Okay, so that's what I store the power of 2. Now, for all the other ones, what I look at is I start reading from the least significant bit and see how many zeros I have. So for 3, there's no zeros. And if there's no zeros, all I'm doing is I store exactly one thing. Okay, so this one has no 0. I just store this, and this one has no zeros, so I just store this. Here, I have something that has 1 0. If I have 1 0, I store 2 things, the sum of 2 things. Which 2? The current one and the previous one together. So it's 5. Okay, so maybe if I go a little bit more, if I have 9 and 10, so 9, it's like this, and then we'll just do A9. If I have 10, this would be A9 plus A10. And then if later on, if I have a bigger array, so if I have an even bigger array and look at the index 12, in 12 is like this. So that means I store that I have 2 zeros. That means I store 4 things. And I would be storing A9 plus A12. Okay, so the number of zeros here, whatever number of zeros is here, raise that to the as the power of 2. So I have 2 here, 2 zeros, so 2 to the 2 is 4. And I add 4 of these things together. Okay, that's kind of the idea. This is a little bit convoluted maybe, but the question is why is this a good idea? Right, so if you want to know what is the partial sum at 1, 2, 4, and 8, the power of 2's, all you have to do is read it. This is a partial sum at 1, this is a partial sum at 2, partial sum at 4, partial sum at 8. You can get it really easily. Okay, what if you want to get the partial sum at, let's see here, 7. Okay, partial sum at 7. So you look at this binary representation of 7, right, 1, 1, 1. So you know that if I just look at this entry, it doesn't tell me everything, it just tells me A7. So I look at this entry, I get A7. Okay, that's not very helpful. But now that I got this entry, what I'm going to do is I'm going to strip off the last significant bit, and now I'm at 6. So I look up this entry, so this is 1. Then I add the 5, but 5 is actually A6 and A5 together. So now things are looking a little bit more promising because I'm only doing one operation. I managed to add 2 more things. And now I clear this bit, and now it becomes this. And when I look at this entry, plus 6, that's the rest of it. So what happened is, what I look at the partial sum index that I want to compute, and I basically pick apart the bits. I look at the number, I look up that entry, and then I clear the rightmost one, and I repeat. And when I clear the rightmost one here, then of course I get zeros and I'm done. And in this way, basically you're using, in this particular array, this tree, different nodes stores chunks of different sizes. And it turns out that when you pick the bits apart, you will be able to find the right chunks. And if you glue it all together, you will get the entire cumulative sum that you're looking for. And because we're always picking apart one bit at a time, every time you're clearing one bit, that means that the number of times you do this cannot be more than the number of bits in n, which is about log n. So that's kind of how you use this representation to find the cumulative sum. What other things should I do? So that, okay, so cumulative sum, that's how you do it. If you want to compute AI, if you actually want to recover what is AI, well, it's just the same as what I talked about before. Look at cumulative sum minus cumulative sum at the previous location. Okay, so basically call cumulative sum twice. And that will get you a particular element, AI. And then the final operation that we care about today is AI plus equals V, right? And then the problem is actually, so let's say you want to say A1 plus equals 5. So you have to go and look at this here and say, which one of these sums has A1, and those are the ones that you have to add 5 to. So this one you have to add 5 to, this one, and this one. Those are the only 4. So how do you figure this out? Basically, it's by shifting bits. And then this, and right, so you look at this one, shifting the 1 bit over, and you'll
Do you
realize
lose them too?
do I lose what?
Oh, we lost you for a second, but
Oh,
you seem to be back now.
Yeah, you're
oh,
good now.
okay. So I don't know what I was saying before I lost. So I talked about the fact that you can compute these cumulative sums in log n time. Did you get that part? Uh-oh.
I think so.
Okay, am I?
Yes.
Okay.
You had. I remember you had up to like you had up to the 14.
Yeah.
Yeah.
Okay.
So
So
you had
if you
written that
want, okay, if you want to
at the
get
least.
well, okay. So then, just to finish this off, in case you didn't hear me say this, the way that this works is you take the index and you basically look at every step. You look at the entry in the tree, and then you clear out the rightmost one. So how many times can you clear out the rightmost one? It's the number of bits in n, which is at most log 2 of that number. So that's why the operation takes logarithmic time. And then I said, I don't know if you heard this, how do you get a particular element EI? Well, you basically compute the partial sum at I minus the partial sum at I minus 1. So you call the cumulative sum function twice, basically. And then finally, how do you do an increment AI plus equals to V? And so if you, for example, you want to increment A1 by 5, then you have to look at all of these entries that have A1 in the sum, and all of those entries need to add 5 to it. But you don't have to add everything because not everything is 5. And it turns out that you can actually recover the indices that you need by bit manipulation as well. So in this case, 1 is 0, 0, 1. And if you just left shift the 1, these are all the values that you need to touch. Right? What about A bracket? If you want to do A bracket 5 plus equals to 5. Well, which ones have this one, and these? Okay, let me use a different color. This one has 5, this one has 5, this one has 5. So those are the 3 that you have to deal with. So there's a way to figure that out. Let me go to the code. So this is the way. This is the code to do this. It's some bit manipulation. I don't remember exactly how this works, but basically this is when you take a negative of a number, that's the 2's complement. So you have to remember what that means, and then you do bitwise AND, and somehow magically it gives you the right thing. Anyway, the point is that you got this data structure that allows you to maintain cumulative sums and allows you to update the array and still have all the cumulative sums updated and everything in log n time. Okay, so that's the Fenwick tree. So before I go on, any questions about what it does? Maybe it's not so important you know exactly how it's handled internally, but have just a rough idea of how it works. It's good enough.
So what is this used for then, like in
Yeah.
everyday
Okay. So,
applications?
right. Okay. So everyday application. One of the things that are most used. I don't know how much it makes sense to you because I don't know if you know this application. Let me see if I can. So does anybody know how data compression works? I don't know if you've ever learned it from any course.
I think I know very basic data compression from like one of my first classes.
Okay. So, okay, without going into too much detail, one of the things that's important is to have some kind of probability or frequency information available for all the possible symbols. So, for example, let's say that let's say you want to send numbers, send a bunch of bytes. Okay, so you want to send a bunch of bytes. So each you want to send a bunch of symbols between 0 and 255. So byte is any one of these values. And if you know the frequency, so if you have like a table of frequency, like symbol 0, 1, 2, up to 255, maybe you see 0 10 times, and 1 you see a lot, and then maybe 2 you don't see very much, and so on, then you can actually adapt your compression in a way that these ones, the more probable ones, are coded more efficiently, and the less likely ones are somehow coded less efficiently. So maybe symbol 1 you only use 2 bits, and symbol 2 you use 6 bits. But because even though you use six bits for this, because it doesn't happen that often, it doesn't kill you very much, and overall you achieve compression. And one of the things that you need to do in order to do that sort of stuff is actually compute the cumulative frequency or cumulative probability. Frequency and probability are basically the same thing, right? You just divide by a total, and then you would do something like this. And so what happened is you can guess so basically what happened is you can guess in advance what the frequency would be and hope that it's correct, and then you just compress it based on this statistics. And if your statistics is correct, then you have good compression. But it's hard to guess. It's really, you don't know what data you're compressing. So what most people do is to just say, well, let's just pretend that they're all equal, set them to 10 or whatever it is. And then every time you code a symbol, maybe now you see a 1 come in, you can update it and say, now you have one more 1. Maybe now you code it, I don't know, you code 2, so now you have another 1 here. And then maybe you see another 1, so you update this one. But it turns out that most of what you really need is this table to do the compression. And of course, if you update one of these frequencies, then all of these cumulative frequencies will change as well. So anyway, I don't know how much that helps, but this is one place where updating dynamic frequencies and cumulative sum is useful. Let me see.
Now that you drew that out, I do remember doing the frequency compression in like 3620, I think, where we had to like draw out trees for it or something.
Let me see. Oh yeah, look, this is actually in Fenwick trees are particularly designed to implement the arithmetic coding algorithm, which maintains counts of each symbol produced and needs to convert those to cumulative probability of a symbol less than given symbol, blah, blah, blah. Anyway, that's the arithmetic coding is a particular compression algorithm that uses, and it's one of the most commonly used algorithm for compressing things these days. But that's another, actually arithmetic coding was one of the problems in the regional, a simplified version, if you remember. Anyway. Okay, but there are other applications which is actually in problem C and D. So I'll tell you a little bit more. Okay, so problem A is actually not very interesting in some sense, because the only thing they ask you is to do something 5 million times. Each operation either increments a particular entry or asks for a partial sum. So all you have to do really is call the Fenwick tree functions in exactly the way that I coded, right? So the only unfortunate part is that using C++ input output is not fast enough. Even if you use this sync with stdio and equals to false and all that stuff. And I have to eventually switch to CIO, which looks a little bit scary. But I'll just say, if you want to know, just go to my GitHub and see how to use it if you have never seen CIO before. Don't think it's worth teaching you that. So anyway, I read in the number of elements, the number of queries, produce, initialize in a Fenwick tree of size n, all zeros. Then I look at all the operations. I read the operations if it's a plus. Then I just call increment entry at that location for that change. Otherwise, I just ask for the cumulative sum. The only thing that's a little bit funny is that when they give you I, they want the cumulative sum to I minus 1. So you have to be careful that if I is 0, you can't ask for the cumulative sum at -1. So I have to do an extra special case that if I is 0, then I just return 0. If I is not 0, then I return the cumulative sum at I minus 1. But that's pretty much it. The other thing that I had to do was that my Fenwick tree code in the code library was for integers, but in this problem, entries can be up to 1 billion. I can do it 5 million times. So in the worst case, I can try to increment the same entry by 1 billion, 5 million times. And so I need to change them to use long. So I just basically took my code and replaced all the yins to long. But other than that, it is really just an application of the Fenwick tree code. Okay, now the next one is a little bit more interesting. Okay, so what is it more interesting? So let's see. So you have a game with some gems. There's 6 types of gems. Values of these gems are V1 to V6. They lay out n gems in a row. The i's of these are type PI. And with nothing better to do, they make Q queries. In each query, one of these 3 things can happen. They can change the type of a gem. They can change the type of a gem to a new type, PI. They can decide that all of these, whatever type the gem is, all of the values change to new value. And they also can ask for the total values of the gems from some left point to the right point inclusive. Okay, so there's all these input output format. But basically the idea is here you have 8 gem, you have 5 queries. The 6 types of gems have these values: 10, 30, 25, 420, 39, 69. The 8 gems, the types are 5, 5, 5, 1, 3, 6, 4, 2. Then the first query is type 3. They ask what is the value of all the gems from position 2 to 6. So you have to figure that out. Then 116 means that you want to change the first gem to type 6. This says type 6 is now 3286 instead of 69. And then you ask for some queries again. Okay, so that's the problem. So again, you see the kind of I guess the flavor. There's some, you have a bunch of queries in an array of some kind, and you want to keep doing things like updating things, changing things, or asking for some of things. Okay. Now in this case, it is actually a little bit tricky because there's 6 different types of gems. So I'm going to make things simple in my explanation and pretend that I only have 2 types of gems. Having 6 types, it's really the same thing. You just do the same Same thing, instead of 2 times, you do it 6 times. Okay, so let's imagine that you only have 2 types of gems. So you're going to have an array P, which tells you what are the gems, the types of gems, right? So if I have 6 elements, then that means that the first gem is type 1, type 2, type 2, type 1, type 1, type 2. You're also going to have an array V, which tells you the value of the 2 types of gems. So 20 and 30, let's say. And then you're going to have some operations. Okay, so we're going to have operation 1, change gem, 2, change value, and 3, value from some left index to some right index. Those are the 3 operations you have to know what to do. Now, changing a value is actually really easy because you just go into this array and change it. That's it. So, easy. Change the array. Now, to compute the value of L to R, what you have to do is you have to somehow, if you're given L and R, if you can figure out how many gems of type 1 and type 2 there are, let's call it N1 and N2. So if you know that in a range, there are a certain number of type 1 gems and a certain number of type 2 gems, then you can just basically multiply this by V1. That would be the total values of all the type 1 gems. Multiply this by V2. So I'm using, I guess, 1 base index here. That would be the total values of all the type 2 gem. Add them together. That's the answer. So the question then is, can we figure out how many gems of type 1 and type 2 there are? And then also about changing gems, how do we change gems that will allow us to also keep track of how many type 1 and type 2 there are? And it's actually not so difficult. I'm going to have an array, call it A1, which keeps track of which of these elements are type 1 gem. So type 1 gem. And it's going to be binary. So if it's 1, it means that that position is a type 1 gem. If it's 0, that position is not a type 1 gem. It might be type 2, and if in the original problem, it could be type 3, 4, 5, and 6. Okay. So this is sometimes called an indicator array, and then basically tells you which position it's the elements that you are interested in. Okay, and the rest you just don't care. Now, why is this useful? If I look at the partial sum of this array, it's 1, 1, 1, 2, 3, 3. Now, if I want to know how many gems of type 1 there are, let's say from here to here, what do I do? Well, I can look at the cumulative sum from here. That means that from the beginning all the way to here, there's 3 type 1 gems. But of course, that's not right because I only have 2 here. Why is it not right? Because I also included this one. So if I want to know the partial sum, the number of gems, type 1 gems from L to R, you can compute it as the partial sum at the right endpoint minus the partial sum at L minus 1. So you can remove this partial sum, and then you'll get the right value. Okay, so let's try a different range. Right, what if my range is, let's say L and R here, right? So I take the 3, this 3 minus the 2 here, and that will give me 1. And in this range, there's only 1 of type 1. So partial sums can be actually used to compute not only the sum from the beginning, but the sum of any range. Okay, so what does that mean, right? So how does that help me? Well, if I want to know the value of L to R, and I just use the Fenwick tree to store this array, then partial sum, cumulative sum of R minus cumulative sum of L minus 1 will help me answer how many gem 1 there are. And then multiply that by the value of gem 1 will give me the total values of all the gem 1. What about changing the gem? If I decide, for example, to change this one from 1 to 2, well, that means all I have to do is change this to 1. So I increment with my Fenwick tree, I increment this item to 1. What if I want to change it back, right? So it was 1, but now I want to change it back to 2 or something else. Well, then I just take this 1 and decrement it and change it back to 0. Okay? So basically, if I change a gem to type 1, then I need to increment that position in the type 1 array, the indicator array for type 1, and then have all the cumulative sum and all that update at the same time. Now, of course, if I change from type 1 to type 2 to type 1, I will increment this position in the indicator array for type 1, but I will also have another set of Fenwick tree for type 2. So for that Fenwick tree, I have to decrement. And in general, if I have 6 types, I'm going to have 6 Fenwick trees. And I'm going to, basically, when you change from one type to another, I will have to go in the type that I'm changing from and decrement that value. And the type that I'm changing to, I'm incrementing that value. Okay, does that make sense?
Yeah.
So another common idea, another common application is to keep sort of a number of things, number of items in a range with an indicator array. So indicator array just means that these arrays will only be 0 or 1. 1 means that there's an item at that location, 0 means that there's no item at that location. And of course, what item you keep track of depends on what you're interested in the problem, right? So in this case, I'll have 1 Fenwick tree that keeps track of how many item 1, gem 1, how many of gem 2, 1 for each, 1 Fenwick tree for each type of gem. Now another one, this one is not, I guess this is kind of in problem C and D, is to keep track of current rank. Okay, what does that mean? Imagine I have a bunch of, I tell you that I have a bunch of items. Okay, so start with n things. Okay, so if I tell you, if I have a set of n numbers, what are the operations that you can do? Okay, you can decide to remove k from S, assuming that k is in S, right? If it's not, then nothing happens. You can add k to S. So if k is, if maybe at some point you remove k, and then later on you can add it back. Okay. And now you can say, what is the rank of k at any one point in S. So what do I mean by rank? So in this case, if I ask you what is the rank of 3, the answer is 3. It's the third smallest number. But as you add things and decrease and you remove things from the set, the rank may update, may change all the time. And then finally, you might say, what is the k smallest number in S? Right? As you add things and subtract and remove things from S, this can keep changing. So how do you answer this? How do you do this kind of problem? What you do is you again have an array A. Now, when I say an array A, remember that in a Fenwick tree, this array doesn't really exist. It's sort of a conceptual array that Fenwick tree is used to keep track of the cumulative sum of this array. But this array actually doesn't really exist anywhere in memory. Okay, so I'm going to set up an array like this. 0 is not used, so I'll just put 0. And then this is another indicator array. Basically, it's a 1 if that element is in S, and 0 if that element is not in S. Okay, so basically at the beginning, when we say that everything is, all the numbers from 1 to n is in S, so we just say all of them is 1. Why is that useful? Because the partial sum is 0, 1, 2, 3, 4, 5, 6, 7, 8, up to n. So if I ask you, what is the rank of 5? Well, you just ask the partial sum and we'll tell you it's 5. Now, of course, at this point, it seems kind of silly to ask this question because I haven't done any updating. But if I, for example, decide to remove 4, right? So I remove 4, so this becomes 0. As soon as I remove 4, these partial sums all change, right? 5, 6, 7, n minus 1. So now if you ask what is the rank of 5, the partial sum will tell you the right thing. And this partial sum will be updated as appropriate when things get added and removed. Now, of course, you can also use this array, I guess, to check the values of, you can maybe have a separate array to actually store this so you know whether the element that you're trying to add, it's already in this set, or whether the element that you're trying to remove, it's already gone from the set, so you don't try to do anything illegal. But that's relatively easy to figure out. Does that make sense?
Yeah, that makes sense.
Now, this is a part where that last function that I haven't talked about, get a particular get index largest index. So given a partial sum, call it S, given sum, get the largest index k such that the partial sum at k, it's equals the sum that you're given, right? So if I would say, what is the fifth element? Well, you want to find the index that has a partial sum 5. Sorry, wait, hang on. Yeah, this is a partial sum 5. Let me just redo this because I'm getting confused what is real and what is index. Okay, so if I have this situation, then the partial sum will be like this. So if I want to know what is the fifth item in the set, then I say what is the partial sum entry that has partial sum equals to 5, and it's this one. So number 6 is the fifth number. Now there's a little bit of a trickiness because what if I say what is the third item in the set? Well, if I do what is the third item in the set, my algorithm, my function would give me the largest k that have the partial sum equals to 3, and it will give me this one. But the problem is 4 is not actually there. So you actually want the smallest index, k, that has a certain partial sum, but my code doesn't give that to you. So what you actually have to do is you have to say, what is the largest index that have a partial sum of 2, which is this one, and then you go to the next one. And that will give you the third element. So you have to say, well, what is the largest place that it still has partial sum equals to 1 less than what you're asking for, and then go to the next one. That will give you the correct index. But anyway, that's another common application, is to keep track of the current kth largest item in a set, or either kth largest, or maybe ask for each item, what is this current rank? That's also those are another very common and useful application. Uh-oh. Am I still with you?
We lost you for a second there, but you just came back.
Yeah, okay. My internet connection has been very flaky the whole day. I don't know what's happening. Okay. So now, given that, I'm not going to switch to the problems, but I'll just tell you this next problem. It's called movie collection. And I'm not going to talk about the last one. I'll just let you think about it. Okay, so movie collection says that you have a bunch of movies at the beginning. That the movie IDs are 1, 2, 3 up to n. N is some large number, so you cannot do things brute force. And what you're going to do is you're going to, at each point, you're going to pick a movie. So they're going to tell you which movie you're going to watch. So maybe you're going to first watch movie 4, and then maybe you're going to watch movie 6, and then you're going to watch movie 2. So let's say you only watch 3 movies. So what you're going to do, when you want to watch movie 4, you're going to take movie 4 out. So now your stack is just 1, 2, 3, 5, 6. 4 is out. And when you're done, you put 4 on top. Okay. Then you watch 6. So you take 6 out and you put 6 on top. And then you watch 2 and then you put 2 on top. Okay. So at the end, it looks like this. Oh, wait, I'm missing a 3. 3. And then n, like this. Okay. 7. So every time you pick out a movie, you have to tell me the output requires you to produce how many things are on top of you at that point. Okay, so let's start from the beginning again. Okay, let me write it a little bit. Let me just write 6 things, because what happens to anything else doesn't matter after 6. Okay, so the first movie I pick is 4. So I pick 4. There's 3 things on top of me, so the first number that I output is 3. Then I'm going to erase the 4, and I'm going to move the 4 on top. Then I'm going to watch 6. There are 5 things on top of me, so I output 5. Then I'm going to erase the 6 and put the 6 on top. Then the last movie I'm going to watch is 2. There are 3 things on top of me. Then I'm going to erase the 2 and put it on top. And I can keep going if there are more movies that I'm watching. But that's basically the problem, is that every time you want to watch a movie, you have to figure out how many movies are on top of it. Then you're going to remove that and put it on the top and keep going. Okay, so this is kind of maybe a little bit, looks a little bit different. Why is it Fenwick tree? Why does it have a cumulative sum at all? But one thing that's kind of have the same flavor is that every single operation you have to query something and you have to modify something. And then, so you're answering a bunch of things as you're modifying the data that you have. Okay, so why is this a Fenwick tree, or how can Fenwick tree help us at all? Okay, so we'll just write 4, 6, and 2 here. Those are the 3 movies I want to watch. Now, if I know that I have to watch 3 movies, what I'm going to do is I'm going to actually create an array that is size not 3, not 6, but 6 plus 3. I'm going to have an array that has 3 empty spots that will allow me to put things at the top when I watch them. Okay, so I'm going to have 3 empty spots, and when I decide to watch 4, basically what I'll do is I will have shift this empty spot up like this. Okay, that's my little trick. That's my first little trick, is to allocate an array that's a little bit bigger, so that when I try to move things on top, I don't have to create new space for it. Okay. Now, what I'm going to do is I'm actually not going to store this at all. My array, the array that I'm going to store, well, I guess I don't actually store this array, but the array that I'm going to use Fenwick tree to keep track of the cumulative sum for, it's going to be an indicator array. And it's 1 to mean that there is a video in that position, and 0 if there's no video in that position. So initially it looks like this. And also initially, I will have an array that will tell me. So where did I draw this array? Oh,
You can hear me.
hi. Sorry, I think I dropped out again, didn't I?
Yes.
Okay.
Not for very long though. So.
Okay. So then this is my indicator array, and there's a 1 if and only if there's a movie in that position in my stack. So what does the cumulative sum look like? The partial sum. Well, it doesn't look very interesting at the beginning. It looks like this. Okay. Now I'm going to watch 4. I have to know that 4 is here. Okay, so I have to know where the indicator array just tells me that there's a video or there's no video, but it doesn't tell me what it is. So I have to know that 1 is this, the movie number 1 is in this position, movie number 2 is in this position, and so on. So now I watch 4. How many things are on top of me? Well, it's exactly the partial sum above me. That's the number of things on top of me. So the number of things on top of me is 3. Now, what am I going to do? I'm going to move this 4 up here. So I'm going to move this 4 up here. My indicator array is going to change like this. And my partial sum are also going to change. How is my partial sum going to change? This is going to be 1. Actually, this is going to be 1, 2, 3, 4, 4. Okay, so it looks like this. And I know, and I have to update the fact that 4 is now here. Okay, so I have to know that 4 is here. Now I try to watch 6. Okay, so I look at 6, I know it's here. How many things are on top of me? 5, the partial sum just above me. There are 5 things above me. Now I'm going to move this 6 up to here. So this will become 1. This will become 0. And all my partial sums will change. This will become, all of these partial sums will change now. So this is 1, 2, 3, 4, 5, 5, 6, 6. And now if I want to watch 2, I look at here, look at the partial sum just on top of me, it's 3. So there's 3 things on top of me. So now I move this to here, the indicator array changes again. And then the partial sum changes again. This is 1, 2, 3. Let's get it, make it better. 1, 2, 3, 4, 4, like this. And so I'm kind of basically keeping track of a running rank in some way, just like I was talking about before. And the rank kind of tells me how many things I have on top of me. But the trick here is to create these extra empty spots that I can stick things into when I move things to the top of the stack. And again, I'm using this indicator array to figure out how many things there are on top of me. Because things that are on top of me, if I'm thinking about like the element in the sets problem, it's basically how many elements are smaller than me in some way. It is just kind of the same problem. And so that's another application of this Fenwick tree. The last problem in this set, it's also a little bit tricky, but it's actually slightly easier than movie collection. But basically, it says that they have a sorting algorithm. Okay, what is the sorting algorithm? So you start with an array where all the elements are between 1 to n, and every element happens exactly once. So basically, you started with an array which is a permutation of 1 to n. And then this turbo sort, what does it do? The first thing it does is it swaps the smallest number to the front, okay, by swapping consecutive elements. Then you swap the largest element to the back. Then you swap the second smallest element to the front, then the second largest element to the back, and so on. So, and then basically they're saying, well, how bad is it? How long does it take? How many swaps does it take? And of course, that depends on where the elements are. If you're trying to find the smallest element and the smallest element is in the middle, then it will have to move half of the length. If the smallest element is at the back, you have to move all of it. If the smallest element is already at the first, you don't have to move anything. So I guess beginners might be tempted to just implement the algorithm and count. But the problem is actually that the number of operations, if you actually just count this, do this algorithm and count how many swaps you do, it's actually quadratic. This is actually almost like the bubble sort algorithm. Basically, instead of always swapping the next smallest element to the front, you're kind of alternating. And there's a name for this. It's called shaker sort, and it's basically a generalization of bubble sort, but it doesn't actually do that much better. So anyway, the idea is that if you know where your numbers are, and you know for each number what the position is in the array, you know, do you have 5 things in front of you or 10 things in front of you, you can use that to figure out how many swaps you have to do to get to the front or to the back. And it's essentially the same problem. And you have to use an indicator array that keeps track of how many things are in front of you, and then as you swap things or you swap things into position, you can figure out, you know, which ones are no longer in play, and so on and so forth. So I'll leave the detail to you to figure out. If you can figure out the third problem, this one is actually a little bit easier, I think. So those are the three problems, 4 problems that are related to Fenwick trees. Any questions? Okay, so Fenwick trees is actually quite a powerful thing, and there's actually more things that we can do that I haven't shown you yet. But maybe next time, so I'm kind of on this kind of dynamic data structures. So next time, maybe I'll talk about another dynamic data structure. So what is the dynamic data structure? So data structures, of course, allow you to store data in some way, allows you to access data in some way, whatever those access might be, looking up items or asking for some other kind of computation of the data. But also, you can interleave all of these operations with modifying data. Modify data. And when you modify data, after you modify data, you can access the data again. There might be some other computation that you can do, but the whole point is that you don't want to have to redo all the computation every time you modify data because it could be costly. And so these dynamic data structures somehow allow you to maybe do a little bit extra work to avoid the really worst case scenario. And so in this case, in Fenwick tree, you kind of compute, you store the sum of different chunks of things, and then somehow you can glue the different chunks together in logarithm time instead of always potentially summing up everything in the entire array. So the next time, what I plan to do, I want to talk about something called the square root decomposition. And I want to talk about something called segment tree. Okay, what is the kind of problem that you might want to do? So for example, well, I think you might have seen this before, but it doesn't matter. You might say, okay, you have an underlying array, a from 0 to n minus 1. What can you do? What are the operations? Change AI to something, whatever, AI to some value. You can ask what is the minimum of AI, some left endpoint, all the way to the right endpoint. You might want what is the maximum, and maybe other kind of questions about a range. Okay, so they can ask questions about the range, basically. Could be maximum, could be minimum, could be sum, could be other things. It could be many different functions. So generally, the question then is, if you do a standard way, then answering these could be linear time, because in the worst case, I might ask you, what is the minimum or maximum of the entire array? But if you, for example, let's say you compute somehow, you do some computation and store this in advance somehow, then if you update a value, you might have to update a lot of these pre-computed values. So the question is, how do you balance these two things so that maybe neither of them are extremely fast, but at the same time, neither of them will be extremely bad either. So we'll talk about the square root decomposition. We'll talk about segment tree, and then I'll try to find some problems that also makes you exercise some of these ideas. Sounds good?
Sounds good.
Okay, so
What?
Let me stop the share. Let me stop the